Welcome back. My name is Clayton with the Natural Sciences Tutoring Center at Scottsdale Community College. This video is going to focus on mass spectrometry. Okay, so the IR spectrum, that gives us information about maybe functional groups that are present on a given compound. A mass spectrum tells us the mass, the overall mass of a compound. And for your purposes, I think that's as deep as we need to go with it. You can get the mass of the compound, and that gives you an idea of what kind of atoms might be present as well, like how many carbons, how many hydrogens, right? Things like that. So anyway, what we are going to do, try and keep this video relatively short. I'm actually going to cover two compounds that you guys have already talked about just to highlight what is important about them and why. So that's going to be a benzyl bromide and a benzyl chloride. And then I'm also going to talk about compounds containing nitrogen. Before we really get started into the spectra themselves, mass spectrometry, we should just talk about how it's conducted first. So what you do is you put your compounds into a chamber. The chamber containing your compounds is struck by ionizing radiation, which ultimately just means it's struck by electrons being just blasted at it. What this does is it knocks an electron off of the molecule in addition to fragmenting it. So you end up with a radical cation. A radical cation. So radical meaning you have a single electron hanging out without a pair. Cation meaning it has a plus charge, and so the product of the ionization beam is that you have a radical cation. This is important because the machine itself uses magnets to then get the mass of the particles. So the particles go through this tube, they get turned into something that has a positive charge, and then they're drawn through magnetic force to this plate down here. And then how far or how short they go on that plate is an indication of their mass. Something with a higher mass is going to take more magnetic force to turn like this, and so it will end up being further down on that plate. So things with greater mass. Anyway, that's actually kind of a physics lesson ultimately, but I think it helps to understand how this machine actually works. And so there's a screen that is going to catch these particles as they are spun around through magnetic force. So anyway, that's the general idea. What's important for you to know is that after being struck by these electrons, the compound turns into a radical cation. The radical cation that has the same molecular weight as the actual compound, that's called the molecular ion. That's abbreviated as M+. The compound could also fragment. If it fragments into smaller pieces, those are just called fragments. So now that we have kind of the nomenclature of all of it down, a little bit of an idea of how it actually works, let's get into some spectra. So the first one I have here is a benzyl bromide. So you guys most likely talked about this in lab. I don't know how long ago that would have been, but you would have talked about it, I think. So what is unique about a bromine? We know that bromine has a mass of 79.9. That's grams per mole. Well, we know this is the average molar mass of all the bromines present. And so you actually have like a 50.5% is 79, and then 49.5% is 81. So this would be AMU and AMU. So there isn't actually any bromines that have a mass of 80 atomic mass units. They're either 79 or they're 81. Why is this significant? Particularly, why is it significant that it's roughly a 50-50 split? If we were to zoom in here at our M plus, this is why it's important. Here are the masses, okay? And so this one right here, that's going to be your M plus. This one right here, we can see it's 1, 2 away. That's your M plus 2. These percentages are reflected in the heights. So the height of the peak is an indication of the amount or the abundance, the relative abundance that we would see here. And so if the relative abundance of bromine in the natural world is roughly 50-50 for the 79 mass and the 81 mass, then we would expect when we break apart any given compound that has a bromine on it, that about half of them have the 81 bromine bonded to it and the other half have the 79 bromine bonded to it. That's why we see an M plus and an M plus 2, and they're roughly the same height. And actually, technically, if we really zoom in on this, I don't even know if we can tell. This one should be ever so slightly higher than this one. I don't know if we can even tell just by looking at that, but because technically 50.5 and 49.5, so they're 1% apart from each other, right? Anyway, that is what makes compounds with a bromine unique, is that when you look down here, we'll see, they have, there's an M plus and an M plus 2, and those peaks are roughly equal. That indicates we have a bromine present, okay? So not only do you get the mass of this thing, which here it's 170, we also learn that there is a bromine present within this compound. Now let's talk about the base peak real quick. Each of these peaks, the height of them, again, is a representation of the relative abundance of each of the possible fragments. And so this, because this is has the greatest abundance, that's an indication that it is the most stable. Which is just kind of a side note here ultimately. And in this case, if we were to break this off right here, then we would get this guy. And it's got a plus charge on it because it is a radical ion. And actually it has a little radical on it too, that we're not going to worry about that. This shows resonance with this, if I can draw this correctly. There's 7 sides. Okay, this is how it's drawn. Basically what happens is the ring opens up and accepts this carbon here. And so this is a 7-membered ring. It's called a tropylium ion. And it has a mass to charge ratio. That's what the M per Z is a mass to charge ratio of 91. So this number right there, that's 91. And that's the base peak for this compound. That's pretty normal for a benzyl something to show a base peak of 91 because this tropylium ion shows resonance and is very stable. So that's just a note then on the base peak. Let's move to the next one here, chlorine. So this is a benzyl chloride, and we can see it looks almost exactly the same. We just switched out a bromine for a chlorine. And if we go once again to our molecular ion here, the M plus, we have an M plus right there, and again we have an M plus 2 right here. In this case, we can see this is about 3 times larger than this one. Why is that? Well, chlorine has a molar mass of 35.45 grams per mole. And again, this is an average, right? And so what this breaks down to is 75% roughly is 35, and roughly 25% is 37. And again, that's AMU, atomic mass units. When we're talking about grams per mole, we're talking about an average molar mass. When we're talking about atomic mass units, now we're talking about these specific atoms. These chlorines have 37 atomic mass units because they have 2 more neutrons, it's an isotope, than the 35 AMU chlorines. And so again, this abundance, the 75 to 25, that abundance is reflected here because this peak is 3 times larger than this peak right here. So that's 3 times larger than that. So again, if we see that, the M plus and the M plus 2, we see this relationship, we can say, oh, not only do I know that the molecular ion has a mass of 126 in this case, we also can see that there's a chlorine present because we have an M plus that's 3 times larger than the M plus 2. Once again, if we were to chop this base peak here shows at 91, and that's going to be your tropylium ion once again, so I'm not going to go into that again. All right, the last one here. What I actually did here to talk about that nitrogen rule is I grabbed guanine and thymine, so anybody that's taken a biology class, you know that these are 2 of the base pairs in DNA. So this is generally called a purine. This is a pyrimidine base. That's not all that important. What I want to highlight here is, I'm going to color these. There's 1 nitrogen, 2, 3, 4, and 5 nitrogens in this compound in guanine. In thymine, there are 1, 2 nitrogens. So let's see what impact that has on our the mass of the molecular ion. If I have an odd number of nitrogens, the molecular ion is going to be odd as well. And so if we look at the mass of the molecular ion, it's 151. Sure enough, it's an odd number. That tells me I have an odd number of nitrogens present in this compound. If I have an even number of nitrogens, then my molecular ion is going to be even. And sure enough, right there we have 126 mass of the molecular ion, which is an even number. There we go. So that's the nitrogen rule. Odd number of nitrogens, odd molecular ion mass. Even number of nitrogens, even molecular ion mass. All right, so that's pretty brief. I think that hits all the main points for what you need to know about mass spectrometry. Next video will be on HNMR, nuclear magnetic resonance. Thanks a lot. See you.